This question is about compression and tension. It's about the difference between materials such as concrete, which are very good under compression, and steel, which is good under tension. And it's the idea of the Young's modulus, where you've got Young's modulus equals the stress over strain for a particular material. And a reminder, if you want, the stress, which is all related to the force, use this symbol for it, it's related to the force per unit area, cross-sectional area of the material, for example, so that's the area there. And we're going to put it under a certain force. The force can be a compressive force, a compression, where you're squashing it together. So let's say we've got a block of concrete here. That's a compression, where we're trying to squash it together. And a tension is if we take the same block, but instead of squashing it together, we stretch it apart. So that's the difference. And the strain is equal to how much it changes its shape, really, as a percentage or as a fraction, is equal to the delta x, which is the amount that it changes its shape, and x is the original length of the sample that we've got. Okay, so they give us a graph, and the interesting thing is to say that positive values of strain represent compression. So this is the direction of compression, and this is the direction of tension. So what that means is that if you put a certain amount of stress on it, in the direction of squashing it, this is this direction. So this is what happens in terms of the percentage change. Now you'll notice this is not symmetrical. So the stresses that you put might well be the same, but if you're stretching it out, you notice that there's a big problem there. It doesn't do very much. Whereas on this side, it does quite a lot. What that means is it's much more flexible under compression. And it's basically a disaster under tension. It's going to crumble and break. It crumble, break under tension. Okay, so that's just by looking at the graph, you can see there's a big difference here. That's the sort of stress that you can put on before it. It's hardly any stress at all. It's not even it's about -8 megapascals before it starts really messing around. And then in the positive direction, in the compressive direction, you can get up to about 40 megapascals, which is a lot more, 5 times as much really, before you have problems. So let's look at what they're actually asking for. Explain how the stress-strain graph shows that concrete is more suitable for use under compression than under tension. Well, you've got to make sure you're answering the question, so explain how the graph shows it. So you've got a long region here where this is actually elastic. Elastic is general good, but it's also able, with a very large range of stresses, it's able to be compressed, change its shape for quite a significant percentage, and it doesn't really break until you go beyond about breaking. Well, the maximum stress that you want to put on it would be about 40 megapascals, whereas the opposite is you can only put about even if you say about 10 megapascals under tension. So that means it's about 4 times as much stress it can withstand if you're compressing it. That's how the graph shows it. So the graph shows that under compression, it can withstand about up to 40 megapascals. That's 40 times 10 to the 6 pascals. That's quite a lot of pressure, if you like. And under tension, it can only withstand about about 10 megapascals, or about 10 times 10 to the 6 pascals. So there's a huge difference between stretching it, where it doesn't do very well, and compressing it. Steel is a metal often used in building. The stress strain graph for steel is shown. Now you'll notice that this is symmetrical. So the first thing to notice is that this is again compression and this is tension, but it's broadly symmetrical. So if you stretch it or you compress it, it kind of responds in about the same way. It's got a kind of a yield point really, or the maximum safe stress of around about 5 times 10 to the 8 pascals, which is quite a lot actually. It's a lot of pascals, and this is about 5 times 10 to the 8. So it's pretty symmetrical, which is kind of nice. So what are they asking in this one? A steel rod has a diameter of 45 millimeters. So they're going to be asking us to do some calculations and calculate the maximum force that could be applied to the steel rod before it fractures. So you need to go back to a way to relate stress, which we've got on the graph, with the force. So the stress, by definition, is equal to the force over the area. And so we can rearrange this equation and write the force is equal to the stress times the area. And they give us the diameter just to make us think a little bit. Now, we're talking about a steel rod. A rod looks like this. It's got a circular cross-section. So they give us the diameter, and we can work out the cross-sectional area is pi times d over 2 squared, pi r squared. So we can then read off the graph around about 5 times 10 to the 8 pascals. So 5 times 10 to the 8 pascals times the area, which is pi times 45 millimeters. Pi times 45 millimeters divided by 2, so 22.5 times 10 to the minus 3 meters. And this is the radius now. Square all that. And let's do the calculation. So you've got, I'm going to turn it into meters right away. So 0.00225 squared times pi times 5 times 10 to the 8 pascals. So the maximum force, F, before it fractures is about approximately equal to 7,952 newtons, which let's say it's about 7,950 newtons. Let's go. Really, 2 is probably fine. Anyway, 2 significant figures, right? Okay. To make concrete suitable for use under large forces, steel rods are sometimes embedded in the concrete. Now, this is interesting. So you embed a steel rod. Now, immediately you're thinking steel it's very strong. It's pretty heavy, but it's strong, and it's particularly good under tension when you compare it with concrete. Concrete is a lot lighter. It's also strong under compression. So this combination will be interesting. So let's see what they're actually asking for. An external tensile force is applied to steel rods. Okay, so we've got some steel rods here, and then we pour concrete into a mold around the rods. Once the concrete has set, the external force is removed, placing the concrete in compression. Right, okay, so this is very clever. So explain how this process increases the maximum tensile force that concrete can withstand before it's fractured. Okay, so what happens is the steel is good under tension. So that's one thing. So steel being in there helps the concrete. The other thing is concrete placed initially under compression So if it's initially under compression, concrete placed under compression can withstand greater tensile force than uncompressed concrete. Well, the reason for this is quite simple. If we go to the graph, so let's have a look at the graph now. We go to this graph of concrete. If we place concrete under compression, let's say we're compressing it with about a force divided by area, so it's a stress of about, maybe here, something like 20 megapascals. What that means is that it's starting here, it's not starting at 0, 0. So that means we can put a stretching force, a tensile force, of the difference between the starting point here and where it would normally break, of 30 megapascals before it's going to break, rather than 10. So whatever force we can put, a compressive force on concrete to start with, we're going to enable it to withstand more of the strain in the tensile direction, more of the stretching strain, so it will be able to withstand basically more stress before it breaks. Okay, so let's see how we write that then. So steel, good under tension, that helps anyway, that's good. Concrete placed under compression can withstand greater tensile force than compressed concrete. This means that, and probably say, because the starting position for compressed concrete means a greater stress in the tensile direction, tensile of course, can be placed on the concrete before it fractures under tension, e.g. if compressed by a stress of plus, say, 20 megapascals, and I'm going to write down here anyway, you wouldn't maybe write this long, then it can withstand minus 20 megapascals before returning to its starting point. And that's enough for 4 marks. Right. Next part, explain why the external tensile force in the rods must not take the steel beyond its elastic limit. Okay, so beyond elastic limit, steel does not return to its original shape. And it's the returning to original shape, original length, if you like, original shape, that creates the compressive force on the concrete. So if it doesn't return, it doesn't get as much compressive force. So concrete obviously can't then withstand as much tension. Okay, so beyond the elastic limit, steel does not return to its original shape, and this reduces the amount of tensile stress that concrete can withstand. Basically, it doesn't place it under as much compressive stress at the starting point. Okay, so this is an interesting question, and it's pretty long, but 11 marks. There you go.